All right, hello everyone. Here we're looking at 4.7 day 1, and we're talking about inverse trig functions. Now we've talked about inverses before, and that was when we were looking at functions in general. Like, for example, imagine for a moment, here's a very simple function. Here we have our parabola. There's the parent function of x squared, right? So there it is, vertex at the origin. Now we gave it a vertical line test, and we knew that it was indeed a function. That means for every input there's exactly one output. But if you consider giving it the horizontal line test, it fails. That means there is no inverse. And if we want to graph its inverse, we reflect it over a 45-degree line. So if we would try to do that, we would get this shape. And as you can see, it fails the vertical line test. So this has no inverse. However, we get around this by only graphing half of it. All right, so what you're looking at now is the square root function. So notice we're not taking the plus or minus version. The top half is the plus, the bottom half is the minus. What we did was we threw out half of the graph so that now it does pass that vertical line test. And so what we say is we're just taking a look at the positive version of that square root of x. And we say, okay, that's enough for us to be able to work with. So it turns out that we're going to do something very similar with our sines and cosines. We've spent a lot of time graphing them by hand. And if we were to take a look at the pattern of a sine curve, for example, there it is. And you could give it a vertical line test, and when we draw that vertical line, it crosses the graph only ever at one point. That means, yes, it is a function. That means for every input, there's exactly one output. But it fails the horizontal line test. So here's the graph again on my tracing paper. If we want to take a look at its inverse, we're going to reflect it over a 45-degree line. So here's my line of reflection. We're going to take this and reflect it over that 45-degree line, and it looks like this. This is the graph of its inverse, and it fails the vertical line test, which means there is no inverse. But we want to be able to study some of the properties of the inverse. We're going to do like what we do here and throw out some of the graph. And the result of that is actually summarized down here in the table. So we'll get to that in just a moment. What we're doing is we're talking about the inverses. Now, we're not actually graphing them by hand, but we're using the picture to illustrate what we mean graphically by an inverse. But all of our work is going to be actually just computationally solving problems. We're not actually graphing the inverses, but we're looking at the picture of the inverse in that box down below so that you can kind of see what's happening. We are throwing out some of the graph. And what that means is our answers are going to be more selective. They're going to be restricted to certain quadrants. Here's some other details we need to talk about before we continue talking about the inverse function graph here. So that's what we were just describing in the past. Recall that in order for a function to have an inverse, the graph must pass the horizontal line test. And the sine function does not pass that test, right? If you give the horizontal line test, that means that there is no inverse. However, if you restrict the domain to a certain interval, then we will have an inverse. So like what we've seen up here, we threw out some of the graph. So what should we throw out? Well, we should throw out whatever is causing it to fail that horizontal line test. So if I were to only graph this much of it, then that would pass the vertical and the horizontal line test. We could reflect that over that 45-degree line, and that would do just fine. But it turns out that because this pattern goes on forever in both directions, we can take this sine pattern here and also extend it in the other direction like so. And we're just using this little tail of it. So this much from here to here is what we're keeping. We're throwing out the rest. This much will pass the vertical line test and pass the horizontal line test. And again, you can reflect it over that 45-degree line and see that it does pass the vertical line test. So that's what we're doing. We are throwing out some of the graph. We are going to restrict the domain. And by restricting the domain, that means our answers will come from a much smaller set of numbers. Now, when we restrict that domain and we have the inverse, we call this the inverse sine function. That's what we're talking about down here. But there's two ways that you can write this. The inverse sine function is communicated by this, the arc sine, or this, the sine inverse. So that is not an exponent, it is just a superscript, that little -1 there. And you see that on your calculator too. Right above the sine button, you see the sine to the -1. That's the inverse sine. So you say that as either arc sine or sine inverse. That is your cosine inverse, and right above tangent is your tangent inverse. We'll be coming back to the calculator a little bit later on. So notice it is not the, this is my typo here, it is not the reciprocal. So the reciprocal flips the fraction upside down. It is not the same as 1 over sine. Arc sine and sine inverse are communicating that we are reversing the operation, which means instead of our angle of rotation being an input, the angle of rotation is now going to be the output. It's going to be the answer. So this helps us solve for missing angles. We use the inverse sine when we want to find a missing angle of rotation. So what we're doing here is we're saying, originally, if we were graphing the parent function of sine, we would use the entire unit circle. However, we are restricting the domain. We're not using the entire unit circle. We're using only some of it. And the part that we're using, they're trying to show it here with this little arrow here. We're only using quadrant 1 and quadrant 4. So I'm going to make a note of that in case the color doesn't show up here. Only use quadrant 1 and quadrant 4 of the unit circle. To find our angle of rotation. So remember we said that the arc sine, or the inverse sine, is a way to find the angle of rotation. The angle of rotation is no longer the input, it is now the output. It is now the answer. Where does that angle come from? Well, we can get an angle from quadrant 1 or quadrant 4, but we will never get an angle from quadrant 2 or quadrant 3. And again, so this is the sine curve that would snake its way upwards, but we restricted the domain. So we chopped off the part of the graph that would cause it to fail that vertical line test. So the sine curve would continue like this, kind of snaking its way back up and down. There's your vertical axis. So we threw out all of those parts of the graph so that we could have a graph where we restricted the domain. What that means is our domain is only allowed to be from -1 to +1, because we're on the unit circle and the radius of the circle is 1. And the output, notice the output is in terms of pi. That's your angle of rotation. Now, if we repeat that kind of thinking with our cosine graph, then that means with cosine, we're only keeping quadrants 1 and 2. So that means your domain is the input. The domain is from -1 to +1. And the output, again, we said that your answer is an angle of rotation. So notice that your output is in terms of pi. So anything from 0 to pi. Yep, we're starting at 0 and we're going to pi. That means we will never get an answer from quadrants 3 or quadrants 4. And if we're talking about inverse tangent, then we're back to using only quadrants 1 and 4. There's its graph. Again, remember that your tangent graph was like this, sort of extending downwards and extending upwards, and then when you reflect that over that 45-degree line, now it's extending to the left and to the right. Instead of a vertical asymptote, you now have a horizontal asymptote. So everything is backwards with the inverse. Here, the domain is all real numbers, and the output, the range, again, those are angles of rotation. So, by definition, the values of inverse trig functions are always in radians. That means your calculator, when we use that, must be in radian mode. So make sure that you go to your mode button and you turn it into radians instead of degrees for a few of the problems. Most of the time we're going to try and use the unit circle, but occasionally we end up using the calculator, and that has to be in radian mode. So the first thing we're going to do is we're going to practice writing this in inverse form. These examples are not on the printed note packet that you may have. I added these in later. So if you don't have them, here they are. We'll take a look at these three. Let's write in inverse form. Now remember, this is cosine, and we've learned in the past that cosine at a certain angle of rotation gives you a point on the unit circle that is paired up with your x-coordinate and sine with the y-coordinate, right? So we're thinking of the unit circle now, and so we are thinking of pi over 2. So quick sketch, there's your unit circle. There we are at pi over 2, and that coordinate point is 1, 0. Excuse me, that is not correct, 0, 1. Let me try that again. So notice that we're not solving for anything here, we're just making a true statement that the x-coordinate on the unit circle at pi over 2 up here is 0. There it is, once I fixed my mistake, there's the little 0. What we want to do is we want to write this in inverse form, and in inverse form we can either use arc cosine or we can use cosine inverse, so it doesn't matter which way we do it. We could say arc cosine. Now remember, the inputs and outputs always get exchanged. So what used to be an output is now an input. We're saying arc cosine of the 0 coordinate gives me, and remember we said that the answer to an inverse trig function is always an angle of rotation. There it is. So your answer is pi over 2. That's the angle of rotation. Now we could have used this notation, we could have used cosine inverse with that little superscript. Again, notice that's not an exponent, that's just a superscript. We're saying inverse cosine or cosine inverse of 0 equals pi over 2. So you could write it either way. Here's another example. Cosine of pi over 6 is root 3 over 2, right? Think of your unit circle. There's our angle right there of pi over 6, and that coordinate point is root 3 over 2, 1/2. So again, we said that cosine is paired up with the x-coordinates. We're saying at this angle of rotation, where the angle is your input, the x-coordinate on the unit circle is root 3 over 2. Right? So there it is. Now if we write this in its inverse form, cosine inverse, then we have to exchange inputs with outputs. So we're saying cosine inverse of root 3 over 2 equals, and again your output is always an angle of rotation now with the inverse. So we're saying that the x-coordinate, when my x-coordinate is root 3 over 2, gives me an angle of rotation of pi over 6. Here's one for sine. Now notice this is already in inverse form, and notice the output is pi over 3. So think of your unit circle. When you are at pi over 3 on the unit circle, this is the y-coordinate. So to write this in its inverse form is to write it in its regular form. So this is sine, without the inverse, at pi over 3 equals root 3 over 2. So notice again, what's happening here is the inputs and outputs are changing places. That's the case whenever we have an inverse form. All right, let's go on to the next page here. At the top of the page it says, find the exact value if possible, otherwise approximate with a calculator. So in other words, when it says find the exact value, that means use the unit circle as long as we have a value on the unit circle to work with. But if we have a value that is not on the unit circle, well then we'll go to our calculator and make sure that's in radian mode. All right, so for example, this is saying arc sine of that root 3 over 2, that is the y-coordinate, and the answer to this arc sine is always a theta, an angle of rotation. So the question is asking, where am I on the unit circle? What angle of rotation will I be at when my y-coordinate is root 3 over 2? All right, so that's what we're asking ourselves. So again, recall that the sine is paired up with your y-coordinate, so we know this is a y-coordinate. So think to yourself, where are we on the unit circle? What must my angle of rotation be such that I get a y-coordinate of root 3 over 2? So that answer is pi over 3. Now if you take a look at the unit circle and we're looking at this angle of pi over 3, we see that here, right? Sure enough, there's the y-coordinate of root 3 over 2. But what about quadrant 2? Here's another place on the unit circle where our y-coordinate is root 3 over 2. Why can't I use 2/3 pi as well? Well, we have to restrict the domain. Remember that we're only using quadrant 1 and quadrant 2 of the unit circle to find that angle when we're talking about our inverse sine. Inverse cosine, we're only using quadrants 1 and 2, and a tangent is quadrant 1 and 4. So this is quadrant 1 and 4. I think I said 2 earlier. This is quadrant 1 and 4 that we're using whenever we're trying to find an angle of rotation for that inverse sine. Inverse cosine is 1 and 2. And so what we're doing here is we're saying, okay, I want to find a y-coordinate that's at that root 3 over 2. And even though we have two possibilities, I can't use the one from quadrant 2. My inverse sine only is going to work on the right side of my unit circle. And all of these y-coordinates are negative in quadrant 4, so I'm not going to select any of those. I'm selecting only the positives because I have a positive. All right, let's look at some other variations here. So this is again an inverse sine, and the question is asking what will that angle of rotation be when my y-coordinate is 0. So again, think of your unit circle. Where would we be on the unit circle? And we're only using quadrants 1 and 4, where my y-coordinate is 0. All right, do you know it? Our y-coordinate is 0 here. There it is at 0 pi radians. So our angle of rotation is, in fact, 0. But keep in mind that's 0 radians. That 0 up there is the y-coordinate. All right, here's another one. Number 3, the inverse sine of 3.5. Okay, we have not seen that number on the unit circle, so we are certainly not thinking of that in the unit circle. But I want to go back to the previous page and remind us about the inputs, the domains. If we're talking about sine, the domain is -1 to +1, meaning I can only find outputs if my inputs are going to be between -1 and +1. In other words, this example is giving us something that has a number that is outside the domain. So this answer is undefined, meaning there is no angle of rotation. Right, so as a note, 3.5 is outside of the domain. Recall that the domain has to be between -1 and +1 for our inverse sine function. And if you don't believe me, let's see what the calculator says. All right, let's see if we can take that inverse sine, there it is, inverse sine of that 3.5. And that gives me an error message, meaning it's outside of the domain. All right, here's arc cosine. So in this example 4, now we're thinking about the x-coordinate. And notice our x-coordinate is negative. So with the arc cosine, we can take angles from quadrant 1 and quadrant 2. Well, if it's in quadrant 1, our x-coordinate is positive, and if it's in quadrant 2, our x-coordinate is negative. And that's exactly what we have. We have an x-coordinate that is negative, a negative root 3 over 2. So again, when you're trying to evaluate the inverse trig function, the output, the answer is always an angle of rotation. So the question is asking, where are you on the unit circle? What is your angle of rotation such that your x-coordinate is a negative root 3 over 2? Right? So we're looking at our unit circle. There's our quadrant 2. There's our x-coordinate of negative root 3 over 2. That's at 5/6 of a pi. And again, just a little note here, the theta that we're trying to find, the angle of rotation that we're trying to find, can only be from quadrants 1 and 2. As opposed to our sine curve, our arc sine rather, here our angle of rotation can only be from quadrants 1 and 4. All right, let's look at a few other examples. Here in number 5, we have an arctangent of 3.2. So that is clearly not a number on our unit circle at all. So that means we go right to the calculator. Remember to set your calculator in radian mode. And so let's type that in. We want the arctangent. So again, that's going to be our inverse tangent button. So second function tangent pulls up that inverse tangent button of the 3.2. I hit too many. Let me try it with that one more time. And there's our answer, 1.26. We'll go to 3 decimal places. So 1.268. 1.268. Now again, that's in radians, so that's an angle of rotation. Now you might look at that and say, wait a minute. When I was trying to do inverse sine, I couldn't type in 3.5 because that was outside of the domain. Why does it work for inverse tangent? That is kind of a strange situation, but that's because the graph of this inverse tangent goes forever to the right and to the left. That means the domain is anything. That means the domain is all real numbers. You can plug in anything you want. But with the sine and the cosine, the inverse sine, the inverse cosine, we were limited. We had a very restricted domain in that case. With inverse tangent, we can plug in anything we want. So that's all real numbers, even 3.2. All right, here's arc cosine of -1. All right, so think of your x-coordinates. Where are you on the unit circle where your x-coordinate is -1? That is exactly pi. Remember, with arc cosine, you can use quadrant 1 and quadrant 2. This is a quadrant angle right at the base of quadrant 2. Again, that's in radians. All right, so here we have inverse tangent. Now, if you think about this for a moment, recall that tangent is sine over cosine. And we describe that as the y-coordinate over the x-coordinate on the unit circle. So what we're thinking about is when I do my y-coordinate over the x-coordinate, the result is 0. And we want to know what angle of rotation must we be at where the y-coordinate over the x-coordinate gives me an answer of 0. So it helps to sketch out a little mini unit circle. Again, with inverse tangent, we're only allowed to use quadrants 1 and 4. So these are the 3 quadrant angles. Here we are at 1, 0. Here's 0, -1 at the bottom, at the top. 0, +1. So the question is, when you go y over x using these 3 possibilities, we don't want an undefined result, we want a 0 result. And that means we're going to be right here. We'll take the y-coordinate of 0 divided by the x-coordinate of 1, and that gives us an answer of 0. So what we're saying is that the inverse tangent, when that ratio is 0, gives me an angle of rotation at 0 radians. So this is 0 pi radians. So this 0 is the ratio of the y and x coordinate, but this 0 is the angle of rotation, right? The inverse tangent always gives you an output that is an angle of rotation. And again, remember that our angle of rotation, our theta, for our inverse tangent can only be from these 2 quadrants, quadrant 1 and quadrant 4. Now notice here we just used the calculator. We weren't thinking about quadrants necessarily, but that's because this value was not in the unit circle. This is on the unit circle, and that's why we did not use the calculator. On the homework, all of the problems will be set up like this type, where you will be using the unit circle. You won't be using the calculator on that set. But continuing on with the examples here, you can see we do have a calculator problem in number 8 because this 0.2447 is not on our unit circle. So we go right to the calculator and just type that in. And again, that answer is in radians. Last one here, inverse cosine of pi. Now they're trying to trick you here because remember your input has to be a certain value. For inverse cosine, your inverse cosine has to be between -1 and +1, and your output is an angle of rotation in terms of pi. This, they're trying to say, hey, plug in an angle of rotation. Well, you can't. Your inverse cosine will give you an answer in terms of pi. You can't plug in pi. So this is just bad form. Essentially what it's saying is, what is the inverse cosine at this value of 3.14? Well, that's outside of our domain, right? Our domain, much like what we saw here for inverse sine, has to be between -1 and +1. 3.14 certainly outside of that, so the answer is undefined. Again, pi is outside the domain. And if you weren't sure, you could plug that in your calculator and it would give you that error message as well. So that's the bulk of what we're doing here. We do have some more examples to go through, but that's the main piece of what we're looking at. We have to be able to use not just use the unit circle in terms of looking at it, but you need to know the unit circle well enough that you can recall this information from memory. When to use the unit circle and where you are on the unit circle to find those angles of rotation. So that's the first significant piece. These next couple of problems, we're switching gears. We're stepping away from the unit circle. We're using the trig functions to create ratios of sides. We're thinking of SOHCAHTOA in this case, and I want to add in another extra example by hand in here as well, just to kind of fill out a wider variety of examples. So, when it says use an inverse trig function to express theta in terms of x, that doesn't mean we're solving for x. That doesn't mean we're solving for theta either. It just means we're writing an equation where we have an input and an output. Theta will be the output. That's the variable we have to get by itself. X will be the input. Now here we have a right triangle, and here's our reference angle. We have two sides identified, but not all three. That's okay. We're just using the two sides. So is this sine, cosine, or tangent? Right? This is your adjacent leg. This is your opposite leg. And you want to think of your SOHCAHTOA to help you remember whether to select sine, cosine, or tangent. The opposite and the adjacent sides combine to form the tangent ratio. So tangent of the reference angle equals that ratio of x plus 1 over 10. Now we're not quite done here, because when it says express theta in terms of, that means you have to get theta by itself. So we have to get theta by itself because that has to be the output and x has to be the input. So how do we get theta by itself? Well, we have to get rid of tangent. How do you get rid of tangent? You use its inverse. So the way we show this is we take the inverse tangent of both sides of the equation. And so you can see I'm using a different color there just to kind of show you that we're doing the same operation to both sides. The inverse tangent will cancel out the tangent on the left-hand side, and that's how we get theta by itself. So this is theta in terms of x. So again, we're not solving for x, we're not solving for theta. We don't have anything to plug in as an input, but notice that if you had a number for x, you could plug it in, and the output, the answer, is an angle which would tell you how many radians that angle is. Let's try another one. Here in example 11, we're going to find the length of the third side in terms of x. Then we'll find theta in terms of x for all three of these. All right. So first, let's find the length of the third side. So with a right triangle, we can use our Pythagorean theorem. And while we usually throw down an x as a variable to represent the missing side, don't do that here. We already have an x. If you call this x as well, then you're telling me it's an isosceles triangle with two legs the same size. And they're not. So just call it a until we figure out what the length of a is. So this is my a squared plus x squared equals 3 squared. So a squared plus x squared equals 9. Now we're trying to solve for a, trying to find that third side. So a squared equals 9 minus x squared. And then take the square root of both sides, we can represent a. So a equals the square root of 9 minus x squared. That's the length of the third side, square root of 9 minus x squared. So a couple of things to point out here. First of all, do not try to simplify this. You cannot take the square root of 9 because we learned a while back that as long as you are multiplying, then you can take the square root of each individual factor. That simplifies. But if you are not multiplying, if you have a plus sign or a minus sign, then it does not simplify. All right? So don't freak out and think that you're supposed to take the square root of 9. You can't because of the form. Notice also that we're not really solving for x. We solve for a in a sense that we got a by itself, but it's not represented as a number. It's represented in terms of x. So when you see that phrase, in terms of, what that means is the x is the input. The a is the output. So now we have all three sides in terms of x. So we're using this, we're not using the a anymore, to set up our three trig ratios. So once again, here's the adjacent side, here's the opposite side, here's the hypotenuse. The sine ratio, sine of theta, is opposite over hypotenuse. Okay, but the way they're asking us is they want you to find theta in terms of x, so get theta by itself. So that means you have to take the inverse sine of both sides, and now it's like this. Theta equals the inverse sine of x over 3, the opposite over hypotenuse. Cosine is your adjacent over hypotenuse. So that's the radical 9 minus x squared all over 3. Again, we want to format it in this way. So find theta in terms of x. Get theta by itself. Undo cosine with the inverse cosine. And there's your fraction. Lastly, tangent. Tangent is opposite over adjacent. Now, you're going to notice we have a radical in the denominator, and normally we would rationalize, but not this time. We are not going to rationalize, and this is the only time we don't, and that's because we clearly want to see what the two sides are, so we can say, hey, this is the opposite side, and this one is the adjacent side. If we rationalize it, then we lose track of which two sides we're actually comparing because we're changing the form. So that's easy for us. Don't rationalize. Let's take the inverse tangent of both sides, and we end up with the inverse tangent of that fraction. That's the ratio of our two sides. All right, so again, this is your key phrase where it says, find theta in terms of x. Whatever comes first, that's what you have to get by itself. So you have to isolate that variable. So that's your output. So x is your input, theta is your output, and that's what you have to get by itself, and we did. Okay, one final example, and I'm going to try and fit that in right here next to example 10. Let's complete the equation. Now, actually, the work is very similar to what we've already been doing here. It's just going to look different. Here is arctangent of 14 over x equals arcsine of question mark. So we want to figure out what goes in the question mark. Arctangent of 14 over x equals arcsine of what ratio? Remember, sine is a ratio. What ratio do I need? Well, that's a ratio of two sides. Two sides of what? Of a right triangle. So every time we're always coming back to the right triangle if we're not on the unit circle itself. And so you're going to use this information to create a right triangle. Here's a little diagram. There's your reference angle theta. There's your right angle. And the ratio that they give us is what we're going to use to label two of our sides. Remember, tangent is the ratio of opposite over adjacent. So using that ratio, we now know that we'll put 14 on the opposite side and x on the adjacent side. So again, this is the adjacent side, this is the opposite side, and of course there's your hypotenuse. So what's the sine ratio? The sine ratio is opposite over hypotenuse, but the hypotenuse is missing. So we need to find that first using the Pythagorean theorem like what we did down here in example 11. So a squared plus b squared equals c squared. So we have x squared plus 14 squared equals my hypotenuse squared. We'll just call that a c. So x squared plus 196 equals c squared. Take the square root of both sides to isolate that c. This is our hypotenuse, which is the square root of x squared plus 196. Now again, like before, don't try to simplify that because of that plus sign there. We don't have factors. We cannot take the square root of that. So our hypotenuse is that square root of x squared plus 196. Now we can answer the question because the sine ratio is going to be the opposite over the hypotenuse. So arctangent of the ratio of 14 over x equals arcsine of this ratio. We said opposite, which is 14 over the hypotenuse, which is that square root of x squared plus 196. So there is the answer.